This is the third part of our lecture on 1.4, and this part is going to be very theoretical and kind of abstract. So don't worry if it doesn't all fall into place right away, but I hope you'll try to follow along the abstract argument that we make. The question in this part is, given an n by n matrix A, when is it true that Ax equals b has a solution for all possible vectors b and Rm? So each vector b will have its own solution, but can you actually solve this no matter what vector you put in the position b, no matter what vector you put from Rm? And the answer to this question is summed up in Theorem 4 from our textbook. Let A be an m by n matrix. The following are equivalent. A, for every b in Rm, Ax equals b has a solution. B, for every b in Rm, b is a linear combination of the columns of A. C, the columns of A span Rm. And D, A has a pivot position in every row. When we say the following are equivalent, what we mean mathematically is that if any one of these four happens to be true, then the others must be true also. Or you could say any one of these implies the other three. And I would say, well, let's go ahead and say proof here. We're going to go through our steps of the proof. A, B, and C are equivalent by the preceding discussion I'd say see the part 2 video from this section. Really the point of that video was we're actually saying that A, B, and C are equivalent from that. But now D is the trickier part, because the statement D seems to have nothing to do or seem very unrelated from the others. And so to bring D into this picture, we will show that part D is equivalent to part A, and then therefore all four are equivalent to each other. The way we're going to show D is equivalent to A is, this is done in two parts. Now this is where we're going to get kind of abstract, and just try to follow along the argument, and if anybody wants to come and talk to me about it, I'd be happy to go over the details. So part 1 is the D implies A portion of the argument. So we're going to assume that D is true. A has a pivot position in every row. And now I want to show that this implies that line A must be true. For every b in Rm, Ax equals b has a solution. So let B be a vector in Rm. to show that AX equals B has a solution. In other words, it's not a no solution, an inconsistent situation. So to find solutions, we must row reduce the augmented matrix, that matrix that we've been labeling A1, A2 to AN, B, but I'm going to write that as just A, B for short. So this is sort of a shorthand. When I put A here, I mean all the columns of A followed by the B column vector. This is not a matrix inside a matrix. I really want to just take the entries of A followed by the entries of B. So we have to row reduce that. And so A, B in its row reduced form will turn into something else. There will be new entries in the position of A's columns. I'm just going to call that U. And B will also turn into something else. So I'm going to call that D in row reduced form. Since A has a pivot position, in every row, then so does U. Because as we row reduce, those pivot positions will be in the same columns. And so D here on the end of the row reduced matrix has no pivot position. Because they're all taking place in the rows of U. Okay? And so D is not a pivot column. Well, by theorem 2, way back in section 1.2, if the row reduced in row reduced form, if the last column is not a pivot column, then the system of equations has a solution. And the system has a solution. So AX equals B has a solution. And what that means is, squeeze it in here, therefore A is true. We have shown that D implies A.